Hello, good evening. Um, my name is Ranjan Bora, and I am one of the teaching assistant in this course, Biomechanics of Joints and Orthopedic Implants. This course is instructed by Professor Sanjay Gupta from IIT Kharagpur, and today is the last tutorial for this course. Today, I'm going to do the revision of all the concepts which we have learned so far, starting from the week one. And after that, I will solve some numerical problems using those concepts. So I will start now. So first concept is force, which I discussed in my first week tutorial. So what is a force? A force represents the action of one body on another body and is generally characterized by its point of application, its magnitude, and its direction. See, you can see these are some examples of different force which acts on our body during different activity. So in this first case, when a person is doing some exercise using his hand, you can see these are the forces which are represented using the arrows. So the weight of this dumbbell, it is acting in the downward direction. It is shown with the black arrow, and this red arrow, it is showing the force which acts because of the weight of the forearm. Uh, and this green colored arrow, it represents the joint reaction force which acts at the humerus and which acts at the elbow joint. And this blue colored force, it is due to the muscle forces um, because of the excitations on the muscles, which is the excitations is because due to this due to this weight W, means the weight of the dumbbell, since the person is holding the weight on his hand. So uh, to support the weight, the muscles should act some muscle forces for to hold this weight. So this blue colored one is the muscle forces. And in the second case, you can see when a person is running on the ground, these are different forces which act on the knee joint. This first one is the shear force, then there is the knee joint reaction force, and another one is the compressive force. Similarly, in the third case, when we lift some weight from the ground, uh, you can see there are different forces at various joints in our body. Okay, these are some examples of force. And next is moment of a force. What is the moment of a force? So you can see in this figure, a force F is acting at a distance of r, from the center O. So because of this force F, this force will tend to rotate this object about this axis, which is shown using this green color. So this force will tend to rotate this object in this direction, which is shown using this red arrow. And this tendency of rotation is known as moment. So moment of F about O is the vector product of R and F. And it is shown here, M equal to R cross F. Now, what is the vector product of two vectors? So in this plane, we can see there are two vectors, P and Q, and the angle between these two vectors is theta. So the vector product of these two vectors, P cross Q, is given by V, and the direction is First, we will see the line of action of V is perpendicular to the plane containing P and Q, and the magnitude of V is PQ sine theta, and the direction of V is obtained from the right hand rule. So you can see, if we place our fingers along this axis, along the P axis, and if we curl our fingers towards the vector Q, then the direction of this thumb will give the direction of the cross product between these two vectors. So in this figure, you can see the direction of this thumb is pointing upwards. That's why the direction of V is also pointing upwards. Okay. So next is moment of F about O as the vector product of R and F. We have seen this M equal to RF sine theta. Now we can write this R sine theta as D. From this triangle, you can see this is the angle theta. So this is angle theta. So this distance is R cos theta, and this distance is R sine theta. That's why this RF sine theta is written as F dot D. Okay. Next concept is equilibrium of rigid bodies. So when does a body is in equilibrium? So there are some conditions for forces and moments to satisfy for the body to remain in equilibrium. So the necessary and sufficient conditions for the equilibrium of a rigid body are summation of force equal to 0 and summation of moment equal to 0. That means there should be no net resultant force acting on the body if the body should remain in equilibrium. And similarly, there shouldn't be any net moment acting on the body for the body to remain in equilibrium. Next is equations of motion. So what is the equations of motion? Like these equations of motion states the Newton's law. There are three Newton's laws. So Newton's second law of motion states that an object's acceleration is directly proportional to the net force acting on it. So we can see this summation of Fx equal to mass multiplied by acceleration of center of gravity in the x direction. Then summation of Fy equal to mass multiplied by acceleration of center of gravity in the y direction. And summation of moment about Cg equal to moment of inertia about Cg multiplied by angular acceleration alpha. So next we will see what is this moment of inertia I, the mass moment of inertia. So you can see this is an long object. Means the shape of the object is shape of the object. The object is the length of the object is dominating compared to the other dimensions. So we can see the total mass of this whole object is capital M. Now if we divide this capital M into n small objects, then we can end n small objects, and mass of each small object is represented by small m. So this m1 is the mass of this object, small object 1. M2 is the mass of this small object 2. Similarly up to mn. And now if we want to find the moment of inertia about this axis, which is passing through this point, we'll call it O, passing to the point O. So we'll need to to calculate the moment of inertia, we need to know the distance between these axis of rotation and the center of gravity of the mass. So this small x1 is the distance between this axis of rotation O and the CZ of the mass m1. Similarly, small x2 is the distance between the axis of rotation O and the center of gravity of mass m2. So after finding all the distances from the axis of rotation, we can use this formula to find the moment of inertia of this object. So this m1 x1 square plus m2 x2 square plus dot 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 plus mn xn square. So this I equal to summation of I equal to 1 to small n mi xi whole square. So this definition is the moment of inertia of an object. Now we want to find the moment of inertia about any axis uh, parallel to the axis passing through center of gravity. For example, we'll take one object here, and this is the CZ. So the if we say the moment of inertia about this CZ is I naught, and we want to find moment of inertia about this point, about this point O, about this point X, then what we need to know? We need to know this distance. Let's just take this distance is small x. Then the moment of inertia about this point X is given by I equal to I naught plus m is the mass of this object. Okay, then using the parallel axis theorem, we can find the moment of inertia about this axis x passing through x equal to I naught plus m x squared, where I naught is the moment of inertia about center of mass, x is the distance between center of mass and center of rotation, and m is the mass of the segment. And the next one is the joint kinematics. So what is the joint? How we can find the joint kinematics from the data which we can measure in the gate lab. So in the gate lab, we can measure the kinematics data or the displacement or the coordinates of different markers which we can place on our body to perform different activity. So after getting the coordinates, then we can use some theorem for finding the velocities and accelerations. So using the central difference approximation, the linear velocity along the x direction at the ith time instant is given by Vxi equal to xi plus 1 minus xi minus 1 divided by 2 delta t. What is xi plus 1? Xi plus 1 is the displacement at the I plus 1th time instant, and xi minus 1 is displacement at the I minus 1th time instant. So similarly, we can use the same theorem for finding the linear acceleration. So linear acceleration in the x direction at the ith time instant is given by Axi equal to Vxi plus 1 minus Vxi minus 1 divided by 2 multiplied by delta t. And unit of acceleration is meter per second square. So using these two formulas, we can calculate the velocities and accelerations. And the next is the musculoskeletal model. So the musculoskeletal model is a model of our skeleton with all the muscles, joints, and the bones. So these are the three basic parts for this musculoskeletal model. One is the rigid bodies, in which we represent the bones as a rigid body, and we give the inertial properties for the bones, which are mass, center of mass, and moment of inertia. And these rigid bodies are connected by the ideal joints, which are different joints which are present in our body. For example, knee joint, hip joint, then elbow joint, ankle joint. And these joints are defined using the location and orientation of the joint reference frame. And they are constrained by some joint angles. And these rigid bodies are moved by actuators, which are these red colored ones are the actuators. These are the one-dimensional muscles. So these are muscle lines of action. And again, these muscles are defined using some muscle properties. For example, pennation angle, then optimum fiber length, tendon slack length. All those parameters we use for defining these muscles for a musculoskeletal model. Now, next one is the inverse dynamics method for musculoskeletal modeling. So, purpose of developing the musculoskeletal model is to estimate the joint forces and moments using the inverse dynamics method. So, for doing the inverse dynamics method, we need three inputs. Like we can see we need the anthropometric data, which are the segment mass, length, and moments of inertia. Then we need the marker position data, which we get from the motion capture system in the gate lab. And one data we need is the ground reaction force data. Again, we get this force data from the gate lab. So after getting all this data, we can use the equations of motion, which I have discussed previously. Equations of motion are the summation of force equal to 0 and summation of moment equal to 0. And also we can use the Newton's second law of Newton's second law of motion. And after using those equations, we can find out the joint reaction forces and moments for different joints in our body. So in the inverse dynamics method, we represent the anatomical model using some link segment model. So we represent this foot as using one link, this link number 3 in the second figure, and we represent our femur using our tibia using this link number 2, and we present the femur using this link number 1. So after representing its bone as a link, we can separate these links. And so here you can see this link 3 is separated from link 2 at the ankle joint. And now we can take this link 3 as a as an independent system, and we can draw the free body diagram for this link 3. And from the free body diagram, we can estimate this reaction forces at the ankle joint, Rx3 and Ry3. And in the next step, we can use this reaction force data for solving the reaction force at the knee joint using the free body diagram for link number 2. And similarly, we can do this inverse approach for finding the reaction forces at the hip joint by drawing the free body diagram for the link number 1. Okay. So this was the inverse dynamics method for solving different problems to estimate the joint reaction force and moments. Now, in the next concept which is discussed was the stress. So what is a stress? Stress is the internal force per unit area generated within a material when it is acted upon by external forces. So when some external force P is acting on this bar, and because of this external force, there are some internal force which are getting generated inside the material. So stress is defined as the internal force per unit area. This, you can see this definition here. Sigma equal to P divided by A. So the magnitude of this internal force will be equal to the magnitude of the external force P. And A is the cross-sectional area. Next, what is strain? So when we apply the load, when we apply the one-dimensional axial tensile load for this rod, then because of this applied load, its length will be increased. So we can see in the second figure, its length is increased by an amount delta. So what is strain? Strain is defined as the change in length or increase in length delta divided by the original length L. So this is the definition: strain equal to change in length divided by original length. Now there was this stress transformation matrix form. So what is the stress transformation? So if we know the state of stress for let's say for this orientation X and Y. So if we know the state of stress, let us take sigma X, sigma Y, and tau XY, tau YX. So we know the state of stress for this coordinate system XY. Now if we rotate this element by an angle theta, if we rotate this element by an angle theta in the anti-clockwise direction, and if we and let us say the new coordinate system will be x1 and y1. So this angle is theta. So what will be the state of stress for this new position, which is x1, y1? So we can find that state of stress for this new coordinate system x1, y1 using this matrix equation, which is given by sigma dash equal to this rotation matrix R multiplied by the stress matrix sigma multiplied by the rotation matrix R transpose, where the rotation matrix R is given by cos theta, sin theta, minus sin theta, cos theta. And here theta is considered in anti-clockwise direction. So if the theta is in clockwise direction, then we need to put theta as minus theta here in this rotation matrix. So using this equation, we can estimate the state of stress in the new coordinate system x1 and y1. So next was the principal stress, which is what is the principal stress? Principal stress are the maximum and minimum normal stresses in a state of stress at a point, and these stresses act on principal planes defined by the principal directions, wherein shear stresses are absent. So what are the principal planes? Principal planes are those planes in which there is only normal stress acting. There is no shear stress which acts on the principal plane. That means shear stress is zero. So you can see this figure. So this is the state of stress for a two-dimensional element. Now we now let us say that at an angle theta p from the x direction, this in this new state of stress in this new coordinate system of 1 and 2, this sigma 1 represents the principal stress and sigma 2 represents the principal stress. So how do we find the values for this principal stress? So we know that these equations are for this transform coordinate system. So sigma x1 is the normal stress in the transform protein system x1 y1, and tau x1 y1 sigma y1. So how we can find, how we can from these three equations, how we can get the equation for the principal stress sigma 1 and sigma 2. So for finding the principal stress equations, we need to, because in the principal stress, in the principal plane where there is the principal stress, there is no shear stress. So we need to equate this shear stress tau x1 y1 equal to 0. After doing this, we'll get the this value of 2 theta. So, and if we substitute this 2 theta in the sigma x1 and sigma y1, then we get the so in this we can see this tan 2 theta p. After doing the tau x1 y1 0, we get this equation. Now from this we can find the value of sine 2 theta and cos 2 theta. Now if we substitute the sine 2 theta cos 2 theta in the sigma x1 and sigma y1 equation, then we get this equation for the principal stress, which is given by sigma 1 2 equal to sigma x plus sigma y by 2 plus minus square root sigma x minus sigma y by 2 whole square plus tau xy whole square. So this is the equation for principal stress. Next is we can use the principal stress as eigenvalues. So, and we know that stress tensor is a 3x3 matrix for 3-dimensional state of stress. And for this 3x3 matrix, there are 3 eigenvalues, and they represent the principal stress and 3 corresponding eigenvectors, which represent the principal stress directions. And the non-trivial solution of characteristic equation. This is the characteristic equation, and so from the characteristic, this is the characteristic equation. From the characteristic equation, we know we get the stress invariance. So what is the first invariant? First invariant is I1 equal to sigma xx plus sigma yy plus sigma zz. And second invariant is given by this expression, and third invariant is the determinant of this 3-dimensional matrix. And the principal directions we can find using this equation, where n1, n2, n3 are the unit vectors along the principal directions, and n1 square plus n2 square plus n3 square equal to 1. So these are the direction cosines of the principal plane. N1, N2, N3 are the direction cosines of the principal plane. And one concept was about the stress shielding, bone remodeling. So what is the stress shielding? So when we observe this stress shielding, when means after doing some surgery, when we put an implant inside the bone, in that condition, we observe the stress shielding phenomenon, because the implant, being considerably stiffer than the native bone, carries the bulk of the load, which was formerly carried by the bone. This alters the load transfer pattern across the implanted bone. And consequently, a significant portion of bone which was exposed to loads in intake condition is shielded from carrying the load by a stiff prosthesis in the implanted condition. And this sudden change in stress-strain distribution is known as stress shielding. So from this figure, you can see this massive amount of load is taken by this implant, and very little amount of load is transferred to the bone. So that was all about the different concepts which we have studied in the past tutorials. So now I am going to solve some numerical problems using those concepts. So this is the first problem, as you can see. So in the problem it is given, consider a person wearing a weight boot and from a sitting position doing the lower leg flexion extension exercises to strengthen the quadriceps muscles. Forces acting on the lower leg and a simple mechanical model of the leg are illustrated in figure. W1 W1 is the weight of the lower leg, W0 is the weight of the weight of the boot, Fm is the magnitude of the tensile force exerted by the quadriceps muscles on the tibia through the patellar tendon, and Fj is the magnitude of the tibiofemoral joint reaction force applied by the femur on the tibial plateau. The tibiofemoral joint center is located at point O. The patellar tendon is attached to the tibia at point A. The center of gravity of the lower leg is located at point B, and the center of gravity of the weight boot is located at point C. The distances between point O and points A, B, and C are measured as A, B, and C respectively. For the position of the lower leg shown, the long axis of the tibia makes an angle beta with the horizontal, and the line of action of the quadriceps muscle force makes an angle theta with the long axis of the tibia. Assuming that points O, A, B, and C all lie along a straight line, determine Fm and Fj in terms of ABC, theta, beta, W1 and W0. So this is the free body diagram of the leg which is given. So we need to use this free body diagram for solving this problem. So I will draw the free body diagram here. W0, then W1, and Fm. Fj, Fc, and this is point O. Okay. And these distances are A, B, and C. This angle is theta. And we can see this angle is beta. So, and this angle will be beta. So, and this is the x axis and this is the y axis. So first we'll write the x component and y component of this muscle force Fm. So x component of muscle force x equal to Fm cos theta plus beta, and it will act in this direction. Fmx, and y component is Fmy equal to Fm sine theta plus beta, and it will act in the vertically upward Fmy. Okay, so next, let us take this Fj. It is acting at an angle phi, where phi is with the vertical direction. So again, Fj will have two components. One component will be one component. Okay, let us, if this is Fj, then one component will be Fjx and one component will be Fjy. So what is Fjx? Fjx equal to Fj sine phi. And what is Fjy? Fjy equal to Fj cos phi. See, in the question, we need to find this Fm and Fj in terms of ABC, theta, beta, W1 and W0. So we have studied about the equations of motion and equilibrium of rigid bodies. So if we need to apply here equilibrium of rigid bodies. So one is the summation Fx equal to 0, and so if we do this, then summation Fx in the x direction, what are the forces acting? In the positive x, it is Fjx minus Fmx equal to 0. From here, Fjx equal to Fmx. And we need to use summation Fy equal to 0. From this, we will get minus Fjy plus Fmy. In the y direction, these two forces are also acting, W1 and W0. Minus W1 minus W0. So Fjy equal to Fmy minus W1 minus W0. Okay. And again, we need to apply the moment equilibrium equation. So we will take moment about the point O. So for doing the moment equilibrium, we need to also know the distance of the, we need to also know the moment terms for different forces which are acting. So for this force Fmx, the moment term will be, see, this distance is given A. This distance is given A. So that means this distance is A. So this force Fmx, this, if we take out this triangle, this distance is given A, and this angle is beta. So what is this horizontal component? It is A cos beta, and the vertical one is A sin beta. So from the point O, this moment term for this force Fmx is A cos beta, sorry, A sin beta, because this Fmx is acting here in this direction, Fmx, and for the force Fmy, the momentum will be a cos beta. Similarly, for this force W1, the momentum about point O, the momentum will be, this distance was given B, so B cos beta, and for this W naught, this C cos beta. So now we know all the momentums for all the forces. So we'll take moment equilibrium about point O, summation MO equal to 0. If we do this, and we'll take the clockwise as positive. So if we do this, see about point O, this Fmx is acting, producing moment in the clockwise direction. So Fmx dot momentum is A sine beta, and the Fmy is acting in the anticlockwise direction, minus Fmy dot momentum is A cos beta, and W1 is acting in the clockwise direction, plus W1 dot B, what is the momentum? B cos beta. And W naught is acting in the clockwise direction, C cos beta. C cos beta equal to 0. So from this, now we will substitute Fmx and Fmy. What is Fmx? Is Fm cos theta plus beta dot A sine beta minus Fmy is Fm sine theta plus beta dot A cos beta plus W1 B cos beta plus W naught C cos beta equal to 0. Now we'll take Fm and A outside. Fm dot A, we will write sine beta cos minus cos beta sine theta plus beta plus W1B cos beta plus W naught C cos beta equal to 0. Now we can use this trigonometric relation, which is given by sine A minus B equal to sine A cos B minus cos A sine B. So we can use this relation. Here Fm dot A, this will be sine beta minus theta minus beta plus W1 B cos beta plus C cos beta equal to 0. So from here, beta and beta got cancelled. This will be sine minus theta, which will be minus sine theta minus FMA sine theta equal to. So we'll take this into right side minus W1B cos beta minus W0 C cos beta. So from here we'll get FM W1B cos beta plus W0 C cos beta divided by A sin theta. So we have found one relation. So we have determined FM in terms of ABC theta beta W1 W0. You can see ABC and this here ABC theta beta and W1 W0. So this is the relation for FM. Now we need to find the relation for FJ. So we can use these two equations, Fjx equal to Fj sin phi, Fjy equal to Fj cos phi, and before that we need to estimate this the x component, x and y component of this joint reaction force Fj using these two equations, equation 1 and equation 2. So using equation 1, Fjx will be Fjx will be Fmx, which will be, we need to substitute Fm here, Fm cos theta plus beta, so will be Fm cos theta plus beta. This relation we can write there Fm. And similarly, using equation 2, Fjy equal to Fmy. What is Fmy? Fm sin theta plus beta minus W1 minus W0. Again, we can substitute Fm here in terms of these parameters ABC theta beta W1 W0. So after getting this Fjx and Fjy, we can get the magnitude of Fj, which will be square root of Fjx whole square plus Fjy whole square. And so we will get the magnitude of Fj, and yeah, we will need to estimate that only the determine Fm and Fj. So we will get the magnitude of Fm and Fj in terms of these parameters. I hope this is clear to you. Okay, this is the problem 2, problem number 2. So what is this problem saying? A runner is contacting the ground with the heel. At the time 20 milliseconds after first ground contact, the ground reaction force F is minus 100 Newton, 600 Newton, and 0 Newton. So we need to determine the force at the hip joint at this time point. We have to use the following assumptions. The hip joint is a hinge joint in the sagittal plane. Only one muscle at the posterior side of the hip joint is activated at this time point. The masses of the foot, leg, and thigh are given, and the coordinates of specific landmarks are given. And the active muscle crossing the hip joint is attached at point M and has a direction which is determined by the vector minus 2 meter, 5 meter, 0 meter, and the velocities and accelerations are given. We can see accelerations are 0, 0, 0. So this problem we need to solve using the inverse dynamics method. So first we'll separate the foot from the ankle joint, and next we'll separate the tibia from the knee joint, and we'll separate the femur from the hip joint. So first we'll separate the foot. So in the foot, if we see the mass of the foot is 2 kg, so this mass of the foot will act 2 into 9.8 Newton, and on the foot, the ground reaction force are acting, which is minus 100 Newton and 600 Newton. So minus 100 means in the negative x direction, minus 100 Newton, and in the positive y direction it is 600 Newton. And the ankle joint reaction force at point A. The ankle joint reaction force will draw using, let us take FA and FAX, FAY. Okay, so for this foot, we'll apply the force equilibrium equations, which is summation Fx equal to 0 from this Fax. And the next force acting in the x direction is minus 100. Minus 100 equal to 0. From here, Fx is 100 Newton. And the next equilibrium equation, summation Fy is 0 from this condition Fay plus 600 minus 2 into 9.8 equal to 0. From here, Fay will be equal to minus 600 plus 2 into 9.8 will be minus 580.4 Newton. So the initial directions which we have assumed, direction for Fx is correct, but direction for Fay will be in the reverse direction. So the actual direction will be Fay in the downward direction. So next we'll use this ankle joint reaction forces, and we'll take this leg. We'll separate the leg from the knee joint, and we'll estimate the reaction forces at the knee joint. So we'll take the knee joint, and at the ankle. In the ankle, what are the forces? This Fx In the foot, this fx is in the positive x direction. So in the knee, sorry, in the leg, this will be in the negative x direction, and what this is mainly fx is equal to 100, and it is since the fy is acting in the foot in the downward direction, in the knee, in the leg it will act in the upward direction equal to 580.4, and the mass of this leg is 4 kg. So 4 into 9.8. Again, we'll consider the reaction forces at the knee joint. We'll take Fkx, Fky. So we'll apply force equilibrium equations. Summation Fx 0, Fkx minus 100 is 0, Fkx equal to 100, and summation Fy is 0, Fky minus 4 into 9.8 plus Fy equal to 0. Fky will be 4 into 9.8 minus 580.4, which will be 541.2 Newton. So we have found out the joint reaction forces at the knee joint. Again, Fkx is positive, that means this direction is correct. But for Fky, the direction would be opposite. It will be the downward direction. So now, see, in the question, it is asking the force at the hip joint. So now we'll draw free body diagram for thigh. Mass of the thigh is 5 kg. So we'll draw free body diagram for the thigh. In the knee joint, this Fkx, it will act in here in this direction, Fkx, and Fky will act in the upward direction, and the mass of the thigh is 4 kg, 4.9.8. Sorry, 5 kg. And there is this muscle, the active muscle crossing the hip joint is attached at point M. So this is point M and has a direction which is determined by vector. So the coordinate of the direction is given. From this coordinate, we need to find the unit vectors. So this direction of the muscle, this is point M, and D is given. D is given minus 250, minus 2,5,0. From this vector, we need to find the unit vectors. How we can find the unit vectors? Unit vectors will be minus 2 divided by square root 2 square plus 5 square plus 0 square. And along the y-axis, 5 divided by square root 2 square plus 5 square plus 0 square, and it will be 0. So it will be minus 0.37, comma 0.93, comma 0. So this is the unit vector of this direction of this muscle force. So let us take this muscle force as Fm. And we need to find this angle with the horizontal x-axis. Let us take this theta. Okay, so then what is this theta will be? How we will find this theta? So since this is the x component, means x component of this unit vector, so we will take cos theta equal to 0.37. From here, theta will be 68.3 degree. And what we need to determine? We need to determine the force at the hip joint reaction force. So that also we need to assume. So we'll assume the hip joint force. Let us take this Fhx and Fhy. So here again we'll apply the equations of motion. Summation Fx equal to 0. From this we'll get Fhx minus Fm cos theta minus Fkx equal to 0. Fhx will be Fm cos theta. We need to find Fm also. Fm is unknown here. Plus Fkx. How much is Fkx? Fkx is 100. And one equation, summation Fy is 0. Fhy plus Fm sin theta minus 5 cross sorry, 9.8 plus Fky equal to 0. So Fhy will be equal to minus Fm sin theta plus 5 cross 9.8 minus how much is Fky? Fky is minus 541.2. We'll take only magnitude because the direction we have already considered while drawing the free body diagram. So Fky is 541.2 equal to 0. So now we need to find the magnitude of Fm. So how we will find the magnitude of Fm? So for finding the Fm, we need to use the moment equilibrium about the hip joint, moment equilibrium about hip joint H. So for finding the moment equilibrium, we need to know first to know the moment terms. How we'll find the moment terms? You can see some coordinates are given in the problem. So this H and M, we can see the coordinate for H is this minus 0.3 and 0.9, and coordinate for M minus 0.3, 0.7. So this component, this is 0, and we'll draw using, and this is 0.2 meter. As we can see, this coordinate of H is minus 0.3, 0.9, and coordinate of M is minus 0.3, 0.7, 0.7, and 0.9. From here, we got 0.2. So we got the momentums for force Fm. Now we need to find momentums for weight of the thigh, M of thigh. So Cm of thigh is given minus 0.2 and 0.7. So we need to only consider this momentum, the horizontal component. So it will come from the x component minus 0.2 and h is minus 0.3. So it is 0.1. This momentum is 0.1, and for the Fk force, what is this momentum for Fky will be K, coordinate of K is given, this minus 0.1. So it will be 0.2, and this vertical one is 0.45. So now we know momentum for all the forces. So we'll take moment equilibrium about point H, about the hip joint is 0. From here, first so the horizontal component of Fm is Fmx, which is acting in this direction, Fmx. Vertical component is Fm1. So for Fmx, the momentum is 0.2, and we'll take the clockwise as positive. So Fmx is producing in the clockwise direction. Fmx dot 0.2, and for Fmy, momentum is 0, so it will not produce any moment. We can write Fmy dot 0, then this 5 into 9.8, it is producing in clockwise direction. So plus 5 cross 9.8 cross, what is the momentum? Momentum is 0.1, and Fky, it is producing in the anti-clockwise direction, minus Qy dot momentum is 0.2, Fkx producing in clockwise direction, plus momentum is 0.45 equal to 0. From here, we'll take Fmx dot 0.2 equal to minus 0.5 cross plus FQY. What is FQY? 541.2 multiplied by 0.2 minus what is FKX? FKX is 100 cross 0.45. From here, FMX will be equal to FMX is 291.7. So from this FMX, what is the FMX? FMX is FM cos theta, so we'll get, and cos theta is 68.3. FM cos 68.3 equal to 291.7. From here, FM equal to divided by 788.9 Newton. So we have found FM. Now we can substitute FM in these two equations for finding the hip joint reaction forces. So FHX will be equal to FM cos theta means FMX, which is 291.7 plus 100 will be 391.7 Newton, and FHY will be minus FM sin theta minus 788.9 sin 68.3 plus 5 cross 9.8 minus 541.2. This here will be not. Okay, so if we do this, it is coming minus 1225.2 Newton. So we have found both the X and Y component of the hip joint reaction force. So the question was to determine the force at the hip joint. So we have found both the X and Y components. So now we can use FH, this FH equal to square root of FHX square plus FHY square. If we substitute, then we'll get 1286.28 Newton. So this is the hip joint reaction force for this problem, for this particular time instant. Okay. So there is one more problem related to the stress strain concept. So in the problem, it is saying, suppose a human bone has cylindrical shaft whose preosteal and endosteal diameters are 2 and 1 centimeter respectively. Using the data in the below table, calculate the yield and ultimate load for this bone when loaded in simple compression. Then calculate the torques required to yield and break the bone by twisting it. When the outer fibers of the bone have reached the ultimate shear stress, are the fibers on the endosteal surface above or below reach the shear yield stress? So these are the properties which are given. So first we need to find the yield and ultimate load for when the bone is loaded in simple compression, and the cross section of the bone is this type of cross section. This inner diameter is 1 centimeter and outer diameter is 2 centimeter. So first we'll calculate the yield and ultimate load for when the bone is loaded in compression. So for the yield load, we need to use this value, which is compressible stress and compressive ultimate stress. So compressible stress is given 182 megapascal. We know that stress equal to force divided by area. So from here, we'll substitute the compressible stress 182. This will be equal to Fy, which is yield load for loaded at compression area. What is the area cross-sectional area for this cross section? It will be pi by pi R2 square minus R1 square. R2 is the radius of the outer periphery and R1 is the radius of the inner periphery. So Fy, we need to find Fy. So we'll take Fy to the left hand side. 182 cross pi. What is R2? Outer diameter is 2 centimeters, so radius will be 1 centimeter. We'll take the length unit in millimeter because the stress unit are given in megapascal. Then we'll find the force unit in Newton. So we'll take the outer radius as 1 centimeter, which will be 10 millimeter square minus 1 centimeter inner radius R1 equal to 0.5 centimeter, R2 equal to 1 centimeter. So R1 5 square. So if we do this, it is coming 42.88 kilonewton. The yield load for the compressive yield for the compressible stress is 42.88 kilonewton. Similarly, for the ultimate load, we'll now find the for ultimate load. For ultimate load, we'll use this ultimate stress, which is 195. So 195 equal to Fu divided by pi r2 square minus r1 square. From here, Fu equal to pi 10 square minus 5 square equal to 45.95 kilonewton. So we have solved the first part of the problem. Now we need to calculate the torques required to yield and break the bone by twisting it. So what is the relation for the shear stress when a torque when a torque T is applied? So we have the relation tau equal to TR by IZ. IZ is the polar moment of inertia. So for this cross section, IZ will be pi by 2 R2 to the power 4 minus R1 to the power 4, which will be pi by 2 cross R2 is 1 centimeter. In millimeter, it is 10 to the power 4 minus 5 to the power 4. It will be 14726.2. Unit is mm to the power 4. Now, from this equation, we'll find the magnitude of T or torque, which can be applied for reaching this shear stress, shear yield stress. Shear yield stress is given this 54. So we'll take 54 equal to torque multiplied by R. R, so we should take the outer radius, which is R2. T dot R2 divided by IZ. From here, T equal to 54 cross IZ divided by R2 is 10. So if we do this, then 54 cross 14726.2. It will come 79.521 Newton meter. The torque. This much of torque should apply for reaching the shear yield stress. Now, next question is, when the outer fibers of the bone have reached the ultimate shear stress, are the fibers on the endosteal surface above or below reach the shear yield stress? So we need to check if the outer fibers of the bone reach the ultimate shear stress, which is 69 megapascal, then does the fibers on the endosteal surface reach the shear yield stress? So first we need to find the torque which should apply for the outer fibers to reach the ultimate shear stress. So we'll first find that torque. So ultimate stress is 69 megapascal. So we'll use 69 equal to torque multiplied by R2 divided by IZ. From this, torque equal to 69 cross IZ 14726.2 divided by R2 is 10. So it will be 14746. It is 10,101.61 Newton meter. Now, if this much of torque will act, then what will happen to the fibers in the endosteal surface? That we'll need to find out. So we'll need to find out the shear stress in the endosteal surface when this much amount of torque is applied. Will be 101.61. Again, we will convert the unit of meter into mm into 10 power 3 plus R1. What is R1? 5.5. 5 IZ is 14726.2. So if we do this, then (34.5 megapascal). So we'll see what is the shear stress. Shear stress was 54. So we can see that these fibers on the endosteal surface, they don't reach the shear stress. So this much amount of torque is safe for the fibers in the endosteal surface. So the fibers on endosteal surface do not reach the shear stress. So this was the problem. Yeah, so this was all about the today's class. If you find any doubts, you can mail your doubts to this mail ID. This is my mail ID. So you can mail your queries if you have any. So thank you.